Hello friends, welcome to the One Night Study channel. Today we are going to start our gas dynamics subject. Okay, in this subject we will discuss some important topics about the gas dynamics. So first of all, let's discuss about the three most important type of the equations, which is known as governing equation for the conservation of the mass, conservation of momentum, and the conservation of the energy. Okay, so to find out these three equations, first of all remember in the mind that in order to reduce complexity of the problem, some fundamental assumptions are given. Okay, so here in the gas dynamics some assumptions are given which we have to consider while solving the problems. Okay, so these assumptions are, the first one is continuum. Okay, no chemical changes. The gas is perfect. The fluid is single phase. Gravitational effects are negligible. And the last one is viscosity is negligible. Okay, so these are the assumptions which we have to remember in the mind. Now we will discuss the first governing equation, which is known as conservation of mass. We will derive the uh, equation of the conservation of mass. So now we will start the derivation of the conservation of the mass. Okay, so here we have a fluid domain of arbitrary shape. Okay, like this. Okay, and the fluid is passing like this. Okay, and this is the velocity of the fluid. Okay, and this is our elemental area. Here this is our elemental area. Okay, and here this is our elemental volume. Okay, so this is basically the finite. CV means the control volume. Okay, so finite control volume fixed in space. This is the setup for the finite control volume fixed in the space. Okay, we are deriving the equation for the integral form. Okay, in the integral form, remember this, there are so many forms, that integral form, one dimensional form, and after that 3D form. Okay, so we are deriving for the integral form basically. And here v is the velocity vector of the flow, rho is the density of the fluid. Okay, ds is the control surface area. Okay, so if there is no there is no source of control volume. Okay, in that case rate of change of mass inside the control volume equals to, remember this, okay, difference in influx and outflux of the mass. Okay, just because rho dV is the mass of an elemental volume, hence total mass inside the control volume is given by the rho dV. Okay, this is indication of the closed surface. Okay, now the rate of change of this mass equals to the del upon में del t and this whole term as it is. Okay, and time rate of decrease of mass inside the control volume is given by the negative sign. Okay, now the elemental mass flow across the area ds is given as density multiplied by area of surface multiplied by component of velocity normal to surface. Component of velocity normal to surface. Okay, and it is given by the rho vn ds, which is equal to the simply rho v ds. Okay, and thus net mass flow out of the entire volume through the control surface S is given by closed volume rho v dot ds. Here the v is the velocity of the flow. Okay, now remember this note that if mass flow entering the control volume then take negative sign. Okay, and if mass flow leaving the control volume then take positive sign. Okay, now mass leaving the control volume should be equal to rate of decrease of mass flux in control volume. Okay, so we are not giving the equations number, but you can write in the copy and give the number of the particular equation. Okay, so we have find out the mass leaving the control volume and the rate of the decrease of the mass flux in control volume. Now we will equate these two equations. So we find rho v ds equals to, this is negative sign for the decrease of rate of mass flux, Okay, or we can write this equation, this is z. Okay, del upon में del t close volume rho d volume. Okay, so this equation is the governing equation of the conservation of the mass. Conservation of mass. Okay, now we will derive the equation for the conservation of the momentum. Now for deriving the equation of conservation of the momentum, we have to consider the same diagram which we made for the conservation of the mass. Okay, and assuming that diagram, we will start this derivation of the conservation of the momentum. So this equation is based on Newton's second law, which is equals to d by dt m multiplied by velocity, mass multiplied by velocity, equals to the f. Okay, and here this f is summation of all forces like surface force and the body force. Surface force or and body force. Okay, and we have to find out the right hand side, which is the force, all the forces which is acting on the that fluid domain. Okay, and the m value of the this left hand side term. Okay, so first of all consider the right hand side term. Okay, so here the body force on the elemental volume dv is rho fb dv. Okay, here the fb is the force per unit mass. Okay, force per unit mass, and the p is the pressure. Okay, the total body force in the control volume is given by the, this is the closed integral and rho fv dv. Okay, now the elemental surface force due to pressure acting on the elemental of area ds is, this is the negative sign, and p is the pressure and ds is the elemental, so minus p ds. Okay, negative means force is in the opposite direction of the ds, and hence the total pressure force equals to, this is closed integral p ds. Okay, and the viscous force equals to the f viscous, hence resultant force experienced by the fluid as it is sweeping the fixed control volume is f equals to negative sign p ds plus integral rho fb dv plus f viscous. Okay, basically we have we are summing all the equations which we have find out in the previous equations. Okay, now we will consider the left part of the Newton's second law equation. So now consider the left part, d by dt mv. The mass flow across the elemental area ds is rho fv ds. Okay, hence the flow of momentum per second across ds is this. Okay, and how it is, because the momentum formula is mass multiplied by the velocity. Okay, so this is the our mass and v is equals to the velocity. Okay, net flow of momentum out the volume is the closed integral rho v ds multiplied by v. The momentum of the fluid in the elemental volume d mu, okay, equals to the rho d mu multiplied by velocity. Hence the momentum content at any instant inside the control volume is given by this is the closed integral and rho v dv, and the rate of change due to unsteady flow is equals to del y del t close integral rho v dv. Okay, now we have find out all the essential values of the particulars, the Newton's second laws of the equation. Now putting all the values we get dy dt mv equals to del t close integral v rho v dv plus close integral rho v dot ds v. Okay, so by solving all this equation we get finally this equation which is known as conservation of the momentum equation. Okay, conservation of momentum equation. Now we will find out the governing equation for the conservation of the energy. So in the deriving the equation for the conservation of the energy, first of all let's consider that from the principle of the energy conservation we know that del q plus del w equals to the del E. Here the del q is the amount of heat, okay, and del w is our work done and del is our energy. Okay, so in the term of the rate of the change of these terms, del q upon में del t plus में del 2 del w upon में del t equals del E upon में del t. Now from the diagram which we have made in the starting that fluid domain, okay, so from that diagram the del q upon में del t, okay, the change in the heat flow is equals to the close integral q rho dv plus में q viscous, which is the heat due to the viscous flow, and the work done, change in the work done del w upon में del t equals to the negative sign pv ds plus the close integral rho fv dot v dv plus में work done due to the viscous. Now the change in the energy del E upon में del t equals to the del upon में del t close integral v rho E plus में v square by 2 dv plus close integral s rho v dot ds E plus में v square by 2. After putting all these equation for the del q, del w and del E, we find this particular equation. Here in this equation we have, this is our heat flow, okay, and this is the work done by body force, work done by body force, and this is our, this term is work done by the stress tensor, okay, this is the rate of change of the kinetic energy plus the internal energy. Okay, okay, and this is the net flow of kinetic plus me internal energy. Okay, so this was our whole the equation for the conservation of the energy, governing equation of conservation of the energy. Okay, so friends, in this video we have discussed the three most important governing equation of the gas dynamics: the governing equation for conservation of mass, conservation of momentum and the conservation of the energy. So friends, if you have any query, then please comment in the comment box, and if you have not still subscribed our channel, then please subscribe our channel. Thank you friends.